Yes, please go ahead.
Okay, well, again, thank you very much for having me. I'm very excited to be here, share a bit of my research with you, and be part of this deep learning course for the AMMI Masters. My name is Haan. I'm a research associate at Qualcomm in Amsterdam, and I'm also a PhD student at the University of Amsterdam, supervised by Max Welling, where I work on things related to geometric deep learning and causality. The project I'll be presenting is what we presented last year at NeurIPS. It's called Natural Graph Networks. And the way I'll try to introduce this to you is in a way that how we can apply the techniques that we may use for equivariant deep learning on images and apply those techniques to graphs. And to do so, we need to generalize a couple of concepts, and I hope to take you along the way. I'd like to stress that if there's anything unclear, I'd love if you could speak up and ask me a question. Interrupt me will be great, and we can, hopefully it'll be all clearer that way. This project is a collaboration with Taco Cohen, whom you've seen hopefully these days, and my professor Max Welling. In this talk, I'll first introduce you to graph CNNs, but mostly also what their limitations are. And those limitations are quite profound. I'm not sure if anyone already talked about this, but they are quite remarkable. Then I'll say something about equivariant processing of images, and then how we can generalize that to graphs, and how we put that together in the model we proposed, the natural graph network. So as you know, neural networks on graphs are super useful and ubiquitous. You can use them to analyze social graphs, chemical molecules, or 3D shapes, if we also annotate the graph with something like coordinates. And normally we'd use something called a graph neural network or a graph convolutional neural network, which you probably know by now, but I'll give you a bit of a recap in a way. So what it does, it is a message passing network. And what it does is we start out with features on the graph. So here we have a graph with 4 nodes. We have features at all of those nodes. And to pass a message from Q to P, take the feature at Q, apply some linear transformation, and then at the incoming point, we aggregate the messages into new features. And here we're talking about linear function, but this whole story also generalizes to nonlinear things and even things like attention networks. But it's quite well known since 2017 now that this kind of model is rather limited in what it can do. To make that obvious, here we see 2 graphs that are clearly distinct. They really represent different graphs. And yet, if we would apply such a graph CNN, it would have no way to detect that these graphs are different. And that's because if you would try to put on some feature on these nodes and then you go do message passing, you would see that always all the incoming messages for all the nodes are the same, because this class of graphs is called a regular graph, and the graph CNN is unable to disambiguate between these regular graphs. And this is true for a graph CNN, but even for something more powerful like a graph attention transformer, which you may have already seen. Otherwise, you'll get to know it tomorrow in the lab. So these simple things a graph attention transformer cannot do. So we'd like to fix that. How do we do that? Well, let's take some inspiration from these 2 graphs. So imagine we have these simple graphs, and we have colors on the nodes, and these colors denote the feature values. And then we pass messages to this node and then to that node. And then we'd like to see measure on this node whether these graphs are different. And what you would see is that when we aggregate the messages coming into this node or to this node, it would be the same, 2 dark blue and 2 teal incoming messages. So also this task, a simple graph CNN would fail on. What we'd like to have is that we have some notion that we can remember what the direction is that the information flows through, remember where the messages come from. And kind of comically, we could maybe try to have something like a direction notion in our feature, so that our features are not just scalar values or a vector of scalar values, but they encode some directional notion. But what is it on a general graph? What is a direction? That's not really defined. So what we'll do is we'll take this direction as a bit of an inspiration and see if you can find some analogy that makes sense in the context of a graph that we can use to build more expressive graph networks. So, but let's take a bit of a detour, because we'd like to use these directions and processing of directions to build networks, and that is done often in images already. So here's this amazing animation made by Gabriele, whom you'll hear from Thursday, also a colleague of mine in Amsterdam. And so what they do is they apply equivariant CNNs on images. So if you were to take, for example, this image, and this will be a normal CNN, and we apply a CNN, then we get another image, and we might rotate it back. So we correct for the rotation we apply here, and then we see that while we rotate the input image, the output image transforms arbitrarily. Clearly, this is not equivariant. However, if we look at a equivariant CNN and we rotate the image, then we see also the output rotate. But if we then rotate that back, then we see that we stay exactly fixed. And that shows that this model is equivariant under these arbitrary rotations. So how will we build such a thing? So imagine we want to apply a CNN to this image. And what a CNN in a way does is it cuts up the image in patches, and then it tries to compute for each patch an output feature. So here we would denote one patch, and maybe what we would like here this filter to do that we apply on this patch is detect the orientation of the eye. So here we maybe have the output feature at this point be a direction that points up, indicating the direction of the eye is upwards. And we write a convolution like this. We have some weight kernel, and for all relative distances, it has some value, and then we convolve this kernel over an input feature. We could also write this as a more message passing style to get closer to the graphs. We have inputs at all point Q, so these are the pixels on the image. And then at the output here, point P, we basically apply some message passing kernel on the input, aggregate them, and get the output here this direction. So that if in this case, if we would take one-dimensional inputs, in general, we could have d-dimensional output. So for all pairs P and Q, our weight kernel or message passing kernel is a d by 1 matrix. Now this is an equivariant operation if we would do the following. What we could do is we could rotate this image, rotating both the location and the orientation of the eye, and then apply the convolution again. And this convolution is equivariant if the output here of the original image is exactly the same as the output of the rotated image rotated. And this gives us constraints on these message passing kernels, and if these are satisfied, the kernel is equivariant, or the whole convolution is equivariant. Now we go in the second layer, because we found for each point a direction or an arrow or vector of features. And then in the second layer, we would get for each pixel location a vector of features. So here we have incoming d-dimensional features. And for each patch, we compute an output feature, and that could be d prime. So we could have the same equation here. The message passing kernel is d prime by d matrix. And again, we could have an equivariance constraint, meaning that if we rotate the input image, where we know that we rotate not only the pixels, but also the direction of the vectors, that then rotation and convolution is the same as convolution and then rotation. If this is satisfied, then this second layer would also be equivariant. This is all nice for images, but let's talk about general graphs, because general graphs don't have this nice grid structure. So there's a graph, as you probably learned by now. we can see a graph as a pair. We have a set of nodes. Here we label that by some index, so we can order them in our computer. And the edges are a subset, are pairs of nodes. Now, the equivalent concept of a rotation of an image will be a graph isomorphism. A graph isomorphism is the map between two graphs that is a bijection on the node sets, such that edges are mapped to edges. To give you an example, here we have a graph with indexed nodes. Here we have another graph with indexed nodes. A graph isomorphism maps from the nodes to the nodes, such that when two nodes are have an edge in the first graph, if and only if they have an edge in the second graph. A particular kind of graph isomorphism is a graph automorphism, or a map from a graph to itself, and that we also sometimes call that a symmetry of the graph. For example, this graph has a symmetry, which we get by flipping node 1 and 3, because then we get the same looking graph. So having defined what is the equivalence of a rotation applied to a graph, we could also see what does equivariance look like for graphs. So imagine we have this simple graph, and we have an adjacency matrix of this graph, but we could also have features for each node on the graph. For example, here we have a two-dimensional feature for each node in the graph. And then what we like to do for a graph network is we take some adjacency matrix that encodes what the graph structure is, and also information about the nodes of the graph, and output new features at the nodes of the graph. But note that now observe that this graph is differently ordered, but actually represents the same graph. Also, there is a graph isomorphism between them. Note that we can also relate the adjacency matrix of the initial graph with the adjacency matrix of the second graph by just permuting the rows and the columns of the matrix, and also relate the input features of the first graph to input features on the second graph by just permuting the rows. Also, we can apply a graph network to this matrix and these features and get a new output features on the nodes. And now this operation is equivariant if, again, first applying the network, then the isomorphism yields the same result as first applying the isomorphism and then the network. This is what equivariance in graph networks means. So now let's try to go back to what we previously did. And as we saw, we did message passing on a graph that was an image. Now let's try to generalize that to arbitrary graphs. So we have an input feature at the node Q, and we want to pass a message to node P. And we could do that by having on this edge some matrix that transforms from Q to P. And then for all incoming messages at P, we aggregate the results. But note that this graph and this graph are actually isomorphic graphs, where we rotate the graph from here to here. And what used to be a rotation, we can now reinterpret with this new language also as a graph isomorphism, or in this case, even as an automorphism, because we map from the same graph to itself. And now this whole process of first of computing messages and aggregating the messages is equivariant if first passing the message from Q to P, giving a vector at P, and then transforming this feature along with a graph isomorphism yields the same feature as first mapping from Q to Q prime with a graph isomorphism, and then passing the message from here to here to get the P prime. So if these two paths are the same, then this message passing operation is equivariant. But I have these weird arrows here. I tried to denote some notion of a direction on a graph, but a graph doesn't have directions. A graph is not something that a general graph doesn't have a notion of up, down, left, right. So what could we do to encode something similar in an arbitrary graph? What we came up with is to use neighborhood features. So let's see at this node P. this node P has 9 neighbors. And what we could do is, as an equivalent of having some direction at node P, what we actually do is assign all neighbors of node P some value. And if we have some ordering in our graph, we can stack these into a vector. And so what we say is that actually node P has a 9-dimensional feature associated to it. And previously we talked about equivariant message passing on graphs where we had these arrows. Now we replace the arrows with all nodes have a neighborhood and the neighborhoods have values. Here we see that if we transform with this graph isomorphism from Q to Q prime, that we see that these neighborhood values also rotate. That's the equivalent of the direction we had in the graph. But directions are not really something we can actually do on the graph, but this is something that is perfectly well defined to do on the graph. So the equivalent of rotating this vector at Q is expressed in this case by the fact that these neighbors get different values that look like rotation. And now equivariant message passing is defined as before. Message passing commutes with the graph isomorphism. So first message passing, then applying the isomorphism. It's the same as first applying the isomorphism and then the message passing. So this is how we can do message passing on a graph in a way that is equivariant to arbitrary graph morphisms. But here we have a process that is dependent on what kind of graph isomorphisms exist for this graph. And this graph may be small, but it may also be very large. And it is known that when you have very large graphs, it can actually be exceedingly difficult to figure out what are the ways we can map one graph to another. So what we'd like to do is to have something that scales well, that only cares about small graphs. So what we do instead, rather than looking at the whole graph, we just look at local regions of the graph. Because it turns out that for this previous procedure, we didn't need the whole graph. All we need is a local neighborhood of the message that we are passing, namely of the nodes P and Q. So what we're doing instead, then looking at graph isomorphisms of the entire graph, we look at isomorphisms of this region of the graph. And you can imagine that this graph goes further arbitrarily big. We don't care about it. You can also see that this subgraph is isomorphic to this subgraph, and there is an isomorphism between them. So we say that the message passing is equivariant to isomorphisms of the local edge neighborhoods if for any such local edge neighborhood, mapping it with an isomorphism to another isomorphic edge neighborhood and then applying message passing is the same as first applying message passing and then the isomorphism. So we only really need to look at local regions of the graph, not at the global graph. And that's why this method has the potential of being more scalable than methods that look at the entire graph. So what would this look like? So imagine we have this graph and we want to do message passing on this graph. We have nodes at all, features at all points. And for example, we want to map from this point P to this point Q. Now, if you see that this dark blue region of the graph actually is isomorphic to this dark blue region of the graph, what this constraint that we just show implies is that actually this message passing kernel and this message passing kernel must share weights. Furthermore, we can see that this region of the graph has an automorphism, a symmetry, basically created by swapping these two nodes. As I'll show in a bit, whenever we have such an automorphism of the edge neighborhood, not any matrix, message passing matrix here is allowed, but we get some linear constraints on this matrix. So putting this together to build our model, the natural graph network, what we need to do is we first define neighborhoods of nodes to give us features that look a bit like directions on graphs. And furthermore, to define edges along which we can do neighborhoods around the edges along which we do message passing. Then if the node has NP neighbors, we have some feature that is NP dimensional. So one feature dimension for each neighbor. And you can generalize it with the theory of groups. So we could take an arbitrary group representation of the group of permutations over NP symbols. But for our simplicity, let's just think of these features for now. Then for each edge, we have a message passing kernel. So a matrix that maps from the input node to the output node of the edge. And note that this is important because by now we could have for every different edge a different matrix. So it's very different than in a graph convolutional network that uses the same matrix on each edge. Here we can have potentially on each edge a different matrix. But there are constraints in order to achieve equivariance. Namely, if we have two edges that have isomorphic neighborhoods, and we have linear maps that relate the features at Q to the features at Q prime and the features at P to the features at P prime, then we have a linear constraint, namely passing the message from Q to P and then applying the isomorphism to P prime is the same as first applying the isomorphism from Q to Q prime and then doing the message passing. This is the same diagram as we saw before. So let's look a bit at this constraint. So it means, as we saw, so this is the same in equation form. First applying the isomorphism to from Q to Q prime and then doing the message passing is the same as first doing the message passing from Q to P and then applying the isomorphism from P to P prime. So if we do this about different edges, then we can see that as these matrices are invertible, we can rewrite this, and we see that the message passing kernel from Q prime to P prime is fully determined by the one from Q to P. So they share weights. But when we don't have such an isomorphism, we can have arbitrarily different weights. As I said, this is very different from in a graph convolutional network, which has the same weights on all edges. But when we have an automorphism of the edge, namely mapping the edge neighborhood to itself, we get this equation, which is actually a linear constraint that this matrix KQP must satisfy. What we do in practice is we can analyze this, and with basic linear algebra, we can find out what the solutions to this linear constraint is. And then we can linearly combine these solutions to find arbitrary matrices KQP that satisfy this constraint. And we can linearly combine them with learned parameters, giving us learnable kernels. To give you an example, if we were to pass messages from this point to this point in this neighborhood, which has this automorphism that basically mirrors along this line, we have 9 inputs and 9 output features, so a 9 by 9 matrix. But there's only actually 72 parameters because we need to satisfy this linear constraint. So if we would do this in a computer, what would this look like? Well, we define the neighborhoods. We find out which edge neighborhoods are isomorphic. Then for all these classes of isomorphic edges, we try to figure out what are the symmetries of these subgraphs. Then these symmetries give us these linear constraints, which we solve, and we find and initialize the parameters. And during training, we linearly combine these solutions to the linear equation with learnable parameters. Then we transport the kernel within each isomorphism class because they need to share weights and they are related by this equation. All edges in the same, all edges that are isomorphic. So we can transport the edge kernels within the class of isomorphic edges. And then we can do that to compute the messages, aggregate, and have the convolutional output. This scales well in that this process is linear in the number of edges, but it becomes expensive when the neighborhood sizes increase. So some graphs have very large neighborhood sizes, making this an expensive method. But for graphs, and there's a lot of graphs that satisfy this, that actually have a lot of relatively small neighborhoods. And in such graphs, it scales linearly in the number of edges that we have. What we did before is we had a different set of parameters for each class of isomorphic edges. But sometimes we have something like a social graph where that is very heterogeneous, so very differently looking parts. And if we would apply this basic algorithm, we would get a very large number of isomorphism classes, and that's also a very large number of parameters. So how we solve that in practice would be to treat the message, basically applying the message passing kernel to the incoming feature as the output of some message network. So we have on each edge a network that gives us the output of the message passing. And this network takes as input the adjacency matrix of the edge neighborhoods from P to Q and the input features. And then we have, if we use for K an equivariant graph network, then this whole process becomes equivariant. So basically what we do is we use a graph network on each edge of the graph. And this allows us to find equivariant graph networks without having to solve all of these automorphism constraints and create additional weight sharing between all edges that are not isomorphic. And we can use any equivariant graph network, such as a conventional graph CNN, as the message network, which is computed on each edge of the graph. We can kind of see that this as a hyper network. We have, instead of one graph network, we have a graph network on each edge. We run this on a host of small and large and slightly less small graph classification tasks. And here's a bunch of models. And we find that compared to some other equivariant models, we perform competitively, but these equivariant models, they scale very poorly when the graph grows, whereas our model scales is more scalable because it is a local operation, as it only cares about local regions of the graph, namely these edge neighborhoods. So in conclusion, I think for the first time, introduced a model that looks a lot like an equivariant image CNN, but is applicable to general graphs. We have some more formal theory in our paper where we show that we don't actually need to formalize this as a group, but a generalization of it called a groupoid. And the concept of equivariance in this context would generalize to the concept called natural transformation, which is also the origin of the natural in natural graph networks. So these widely applicable graph networks can now be shown to be more expressive while preserving their efficiency using natural graph networks. Thank you very much. And I would be very keen if there would be any questions or clarities I could address. Thank you for listening.
Great, thank you very much, Pim. So I would allow people who have questions to ask. In the meantime, I would ask a few questions. So the isomorphism, is it kind of a motivation for Kossinen, for instance? So like if you look at the GDL blueprints, you have the first equivariant network layer, which there's some sort of symmetry. Then you get to the local pooling, where you have maybe you think of it this way, like when you have similar representations, learn for maybe some similar subregions that has some sort of isomorphism, and you kind of aggregate them before going to the next layer. Is it kind of a motivation for doing that?
It's an interesting idea. So it wasn't the motivation, but I do see the parallel. The motivation was really more kind of the convolutional layer itself, the equivariant map itself. Yeah, I see. I very much see what you mean, because when you pooling, we can see as a message passing from all higher resolution pixels to the lower resolution pixels in which they aggregate. And we also require this to satisfy some equivariance constraint. Yeah, that's a nice insight. It is still different in that when we have an image or when we have something that has this global group acting on it, we have a more of a notion of direction. So even when we do the pooling, we have a notion of direction, whereas in general graphs you do not. So yeah, there's some similarities and some differences, but that's an interesting insight. Thanks.
Okay, and again, could this be generalized to like directed graphs, for instance? You know,
Sorry,
because
which kind of graphs?
for directed graphs,
Yes,
because
yeah.
you always have directions, and kind of just by flipping one edge direction, it would kind of change the graph entirely. So how?
Yes. Yeah, it is actually directly applicable, and basically what you'd get is slightly fewer symmetries, because in a way directions give some extra information to each edge, and sometimes that breaks the symmetry you would have if you'd otherwise have an undirected edge. So in principle, you could have that the meshes from P to Q will be different than from Q to P. So
Okay.
definitely. Yeah.
Okay, I see. And my last question, so with isomorphism, does it care about the specific node features, or it just looks at the connectivity with the edges?
And that's a very good question. You can actually choose, as in, yeah, that's a great question. So what you could do is, if you would have some, so maybe a discrete label in each node, you could say that, well, the graph isomorphism can never map from green to red, for example. And then you would have a lot fewer symmetries, because you get all nodes are different, and then you have fewer isomorphisms that you're allowed to make. And then you can do the exact same procedure, just with fewer isomorphisms. So you can definitely kind of incorporate the some node features into yeah, kind of incorporate it into how we kind of think of the topology of the graph. You can kind of freely choose whether something is structure or feature. So you have some freedom there. Interestingly, if you look at a paper by Michael Bronstein and collaborators, it's called Improving Expressivity via Subgraph Counting or something. I can have a quick look at the chat. They actually do something very similar. So they improve, they kind of do the opposite of what you propose. So what they do is they extract topological features from the graph and add these as additional features add these as additional features, and then apply a normal graph CNN. And this has some benefit of breaking of fixing some of these expressivity problems, although I believe not all of them. But yeah, so yeah. With all of these things, you can you have some leeway to move from topology to features and back and forth. It's a good question.
Yeah, I see where this is going, but I'm also thinking if you probably have a lot of similar regions in your graph, you could maybe decide to, especially where you have large graphs, you could do some sampling of these unique subgraphs instead. So I'm thinking this is one way it could be helpful, but I don't know in general. If you kind of like have similar subgraphs, you would perhaps want to look at the very unique subgraphs instead. So you could just average the similar graphs out. And in the case where you have very large graphs, that would help with sampling.
Oh, that's interesting. Yeah. Yeah, that's interesting insight. Yeah, if you want to do something like graph sage, or you want to compute graph classification or so, that you would then kind of weigh differently whether a subgraph is common or not. That's an interesting idea. Yeah.
Okay.
I've never tried.
Yeah, so anyone else has a question? By the way, there's a seminar chat room on CampusWire, so you could as well keep your questions there. Pim would answer later when you tag him. And also we are having a tutorial with you tomorrow, right, in the morning?
Yes. Which is the room? Our seminars room is
Yes, there's a seminar. Okay, yeah, you just joined.
Right. Yeah. Okay. I'd be keen to address any questions there.
Okay, yeah. So I would upload the video so people would go through again, and if there are more questions they could ask. Right. So see you in the morning tomorrow.
Yeah, thank you very much for listening. I had a good time.
Thank you.
And yeah, thank you for good questions also.
Yeah, and please share the slides as well. The slides.
Yes. Where would you like me to share them?
You could upload it to the files section on CampusWire.
Okay, will do. Thank you very much. Bye-bye.
All right. Have a nice one. Bye.
You too.